Good morning, friends. It gives me immense pleasure to be here again for my lecture number 36 of aircraft stability and control, and the topic is dynamic stability. Till now, we have discussed about the static stability related to the longitudinal axis, and static stability in lateral and directional axis. Also, we have done with the aircraft equations of motions, and also in our unit 4, we have discussed about perturbation theory, in which we have tried to solve our equation by using the perturb methods. These we have already done. In today's class, I am going to cover about aircraft longitudinal dynamics, then Routh stability criteria, then long period mode, in this stability in supersonic region. In this lecture, I am also going to answer some of the questions like what is the longitudinal dynamics, how to use Routh criteria, and what are the longitudinal modes. These questions I am going to answer in this lecture. Hope this will be very useful to understand the aircraft dynamic stability. Here we have to go first the Routh's criteria. So Routh criteria states that any system can be stable if and only if all the roots of the first column have the same sign, and if it does not have the same sign, or there is a sign change, then the number of sign changes in the first column is equal to the number of roots of the characteristic equations in the right half of the S-plane. That is equals to the number of roots with positive real parts. So this criteria is very important because it says that whether the aircraft is stable or not. So here we have to understand that any system can be stable if only if all the roots of the first column have the same sign. Means in the first column, if all are the plus or all are the minus, it should be in the same sign. And if does not have the same sign, if it is not the same sign, there is a sign change, then number of sign changes in the first column is equal to the number of roots of the characteristic equation. So in the characteristic equation, how many numbers of roots are there? If the changes of these signs are equal, then we can say that it is a system is stable. So here we can see that, let's see this equation. Here we have equation AS to power 4 plus BS Q plus CS square plus DS plus E. This is the fourth order equations. Here A is equal to U1 minus Z alpha dot, B is equal to minus U1 plus Z alpha dot, X1 minus MQ, C is equal to minus Z alpha dot minus M alpha U1 plus ZQ, and the same way D and E also. So here we can see that all the signs of A, B, C, D and E is greater than 0. So this is the condition for the Routh equation. If it is like this, then we can say that the system is stable. We are taking the one case where theta 1 is equal to 0. Theta 1 is equal to 0 means there is no pitching. Okay, it is a steady state cruise flight. For E, we know that E is equal to Q cos theta 1, which we have already seen that E is equal to Q cos theta 1 M sub alpha Z U minus Z alpha MU plus G sin theta 1 MUX. So here we have seen that theta 1 is equal to 0. So this term will be eliminated. So here we will get E is equal to M alpha, and this will be also going to 0. So here M alpha ZU minus Z alpha MU is greater than 0. This condition we have to meet. We know that M alpha is equal to Q1 S C CM alpha divided by IYY, and ZU is equal to minus Q1 S CL alpha plus CD1 divided by M minus Q1 S CLU plus CL1 divided by MU1, and MU is equal to Q1 S C bar CMU plus 2CM1. So if we are now using the case where E should be greater than 0, what is the condition for E should be greater than 0? That is the Ruth criteria. Theta 1 is equal to 0. It means it says no pitching angle or it is in the cruise flight. So if E is greater than 0, and we know that E is equal to M alpha ZU minus Z alpha MU. So E is greater than 0. So this M alpha ZU minus Z alpha MU should be greater than 0. Or M alpha by Z alpha should be greater than MU by M alpha. What additional information we are getting from this equation? When E is greater than 0 means the above expression is greater than 0. So substituting the value in the above equation, we will get that M alpha by Z alpha, putting this value, so we will get here minus M CM alpha by IYY CL alpha plus CD1. Similarly, MU by ZU, putting this value, we will get here that MC, this will be 0. So taking CM1 is equal to 0, we will get these values. So here, taking equation A and B, so from A we will get minus CM alpha by CL alpha plus CD1 is greater than minus CMU divided by CLU plus 2CL1. If we assume here that CD1 is very, very less than the CL1. CD1 is what? It is a coefficient of drag. CL1 is what? It is a coefficient of lift. So if the coefficient of drag is much, much lesser than the coefficient of lift, which is a very good approximation, as CD is much lesser than the lift. So here we are putting this CD1 as a 0. So here we will get CM alpha by CL alpha. It should be less than CMU by CLU plus 2CL1. Here we are getting very good. This is the very good parameter here. So here, what is the meaning of CM alpha by CL alpha? We have seen in the previous our static stability in the unit 1 and 2 that dCm by d alpha by dCl by d alpha. So this is called dCm by dCl, and it is called the static margin. We have seen that, and so many problems we have already. So here this CM alpha by CL alpha we can write as dCm by dCl, and this dCm by dCl is a static margin, and here dCm by dCl should be less than CMU by CLU plus 2CL1. Here we can see that to have the dynamic stable, this condition to be met, for subsonic condition, CMU should be 0. Means there is no slope. If it is for the subsonic, it is going like this. This is the subsonic range. Okay. So this is the CM and this is the U. So the velocity will not change with the coefficient of in the subsonic range. So here dCm by dCl less than 0, and here CMU should be negative. So here CMU is equal to M1 dCm by dm. Here this M is a Mach number. Okay, so here dCm by dCl should less than CMU by CLU plus 2CL1. So what is here CMU? Very important derivative is CMU here. So dCm by dCl, let us assume this is the A, and so this A star should be less than 0 for the supersonic case. So here dCm by dCl less than 0 as CMU is less than 0. So what is here dCm by dCl it is called a static margin. So dCm by dCl is a minus Sm. So dCl by dCl is minus, what is the static margin? It is a neutral point m naught bar minus x Cg bar. It is a difference between the neutral point and the center of gravity point. And so due to this minus, it has become xCg minus neutral point. So here if you see, this is the neutral point and this is the NO. So if we measure from here, so this is the NO, should be more than the, means your neutral point should be behind the center of gravity. Okay. So for the subsonic case, dCm by dCl should be less than 0 or dCm by dCl should be less than A star. Okay. So two cases are here when xCg minus NO should be less than A star. So here A star is negative. Okay. So here we revisit that E should be greater than 0. So in the first case, when E is greater than 0, we got the relationship that dCm by dCl should be less than CMU divided by CLU plus 2CL1. In this, if CMU is equal to 0, it is a subsonic case. So here dCm by dCl should be less than 0 or it is also called the negative. So here this you can see dCm by dCl is less than 0 or the slope of this Cm versus Cl, it should be negative for the to have the static and dynamic stable. For the second case, at high speed, CMU should not be 0. So in this case, if you see, this is the U and this is the Cm. So here, you see here, it should be like this. So from here to here, it is a supersonic. Okay. So here, you can see that dCm by dCl less than A star. So here A star is equal to CMU divided by CLU plus 2CL1. It should be minus 0.1. Let's say it is a negative. So dCm by dCl, it should be negative but with some value. It should not be 0, but it should be some negative value. So for dynamic stability, it should be satisfied this condition. Okay, this is the, so here as speed increases, the aerodynamic center of the wing goes behind and this phenomena is called the tuck under. And this is also called the Mach-tuck number, Mach-tuck derivatives, as the aerodynamic center is going behind. Here we can see with the example that, let's see a business jet airplane with the following data. A is equal to 675.9, B is equal to 1371, C is equal to 549, 5459, D is equal to 86.3, E is equal to 44.78. Here A, B, C, D are the greater than the 0. So here A, B, C, D greater than 0. So roots of these equations, we can see that there are lambda 1, 2 minus 1.008 plus minus J 2.651. This is the short period mode. I will explain this thing in the next slide. What is the meaning and how we can say that it is a short period mode. And lambda 34 is equal to minus 0.0069 plus minus J 0.090. It is called the long period mode or the phugoid. So, two second order system behavior, it is responsible, it response will have two types of oscillation. One is a real root, negative, and this is the large compared to the second pair. This you can see the next, if real root is negative, or form e to the power minus nt. If real root is positive, e to the power plus lambda t. This you can see here. If it is a plus value, it is unstable, and if it is a minus value, it is a diverging. So we should have like this, minus value should be there. So here large negative value indicates decay of oscillation faster than the small positive negative value. So here this, you can see that this is the high value than this. So here this one will be having large decay, very fast decay. So here you can have this type of plot as shown here. It will go and slowly, within a very less time, it will be decay will complete and it will come to the equilibrium condition. But in the long period mode, this you can see the next one. This here the value of this quantity is very less, so it is slowly it is coming like this. It takes a lot of time, so it is called a long period or the Fugate mode. Okay, so in this way we can find out that it is a short period or the long period mode. Now we can also find out the damping ratio and the natural frequency. Here we can see that s square plus 2 zeta omega n s plus omega square n is equal to 0. It is the second order characteristic equation. We can also put this thing that s square minus sum of the roots into s. So these are the sum of the roots. These are the sum of the roots, and this is the product of the roots is equal to 0. So this first this roots omega, this lambda 1 2 is equal to s square minus, we have to use the first equation. So in this 1.008 plus j 2.651, and if you put this value here and then you can solve this thing as a s square plus 2 this minus this, and here a, and if you compare a and b, you will get that 2 omega n is equal to 2 into 1.008 and omega square n is equal to 1.008 plus 2.651j minus 1.008 minus 2.65j. So here omega n is equal to 2.836 radian per second. You see here the frequency which we have got is very high, and here this is the damping ratio. Okay, so if we see the second equation, similarly from the second equation, the omega n34 we will get 0.093, and this is the damping ratio also very less. So we can say that this is the long period and the previous one is a short period mode. So by this we can find out that which one is the short period and which one is the long period mode. Okay, so in this way I have come to the end, and these are my references which I have taken from Nelson book, and thank you very much for joining the class.
Like, share and subscribe. Hit the bell icon for more updates.